In this video, we're going to review integration by parts. Just as the chain rule for differentiation gives rise to substitution in integrals, integration by parts comes from the product rule for differentiation. So let's just first review the product rule. It tells me how to differentiate d dx, a product of two expressions. Let's call them u and v in this situation. Integration by parts says you should leave one of the factors alone. Here I've left u alone, and I should differentiate v with respect to x. I then add and do the opposite thing. I now leave v alone and take the derivative of u with respect to x. So that's our product rule for differentiation. To get an integration formula, I'm going to integrate both sides of that equation. On the left side, if I integrate a derivative, I should get back what I started with. In fact, derivatives and integrals are, in a sense, inverse operations of one another. So on the left side, if I integrate d dx of u times v, I should get u times v back. On the right side, when I integrate these two factors, or these two terms here, I will just have two integrals. I'm going to integrate u dv dx with respect to x, and then add and do the integral of the second term. Now, a principle of substitution says we should do what looks natural, and in fact that means to cancel these dx's in a sense, as treat them as differentials, and we'll do that here and here. So we write this in a simplified differential form, u dv plus the integral of v du. And to get an integration formula, I'm going to solve for one of these integrals. And in fact, I'm going to just choose to solve for u dv, and if I do that, I'll have uv, and I'll need to subtract the other integral to the other side, so it'll be minus v du, the integral of v du. And that's your integration by parts formula. The philosophy here is that you want to integrate this expression here, but you're going to use the integration by parts formula to rewrite it in terms of the integral on the other side. And hopefully the integral that appears on the other side, v du, is easier than the integral that appears on the left side. And if that's the case, you've made some progress. Let's look at some examples next. So let's just record the integration by parts formula in the box there, and then let's look at the example of the integral of x times e to the 3x. Now, a little experience here tells me a good choice here is to take u to be x. If I do that, I have to take dv to be the remaining portion of the integral. I'm going to take it to be e to the 3x with the differential dx. And so dv is a differential, so it should have the dx in it. If I do that, my integral is really x times dv, and so we're trying to choose u and dv to match the left side of the integration by parts formula. If I now look at u is x, its derivative du dx is 1, and I'm going to write that as a differential, so that means du is equal to 1 times dx, or du is just dx. I have dv, and I'm going to need to find v from that. Because it's a differential, it needs to be integrated to find v. So we're going to integrate e to the 3x dx, what we chose dv to be, in order to find v back. And if we integrate e to the 3x, we have to have e to the 3x. It's an exponential function, but we need to divide by a 3, as we talked about in earlier videos. So all of this is on the side, like you do in a substitution, and now we can apply the integration by parts formula. I've chosen u and dv so that my integral is really u times dv. I'm now going to apply this the right side of the integration by parts formula, and in this case it's u times v, x times e to the 3x over 3. That's u times v. And then it's going to be minus the integral of v du. So I look in my box, v is over here, and du is dx. So it's going to be v du there. And you've made progress if this integral here is something simpler. And indeed it is. It no longer has this factor of x in there because of the differentiation. And I now have an integral that's about as hard as the one that we did in the box over here. So let's just clean up a little bit. It's 1/3 times x e to the 3x. I'm just writing the constant out front. And then I'm going to integrate 1/3 times the integral of e to the 3x. No harder than what we just did. Another e to the 3x over 3 for that antiderivative there. And we're pretty much done here. The only thing we can really do is 1/3 times 1/3 is 1/9, and so we'll write that and just simplify the expression. So there's the antiderivative of x times e to the 3x. It's, I think, instructive here to just check the answer. If I want to check that this really is the right answer, I should differentiate it. And if it is the right answer, I should get what I originally integrated back at the end. So let's go ahead and differentiate it. To do that, the first term needs to be differentiated according to the product rule. So I'm going to leave the 1/3 there and differentiate x. That gives me 1. And I leave e to the 3x alone. That's the first part of the product rule. I now need to add and do the opposite thing. The opposite thing means to leave the factor of x alone and differentiate the exponential part. The derivative of e to the 3x is e to the 3x, and then the chain rule says times a 3. I now need to subtract the derivative of this term, and that's 1/9 times another derivative like we just did. Let's simplify the expression. The first term is 1/3 e to the 3x, and then the second term, the 3's cancel out there. And in the third term, a factor of 3 will cancel out to give me 1/3. And if you look at it, the first term and the third term will cancel out to give us e times e to the 3x. Let's look at another example. Let's take the integral of x to the 5th times the natural log of 2 times x. I'm going to take u to be the natural log of 2 times x. I'm going to have to then take dv, if I want to use integration by parts, to be x to the 5th times dx. Everything else that's left in the integral has to now be in dv, and remember, it's a differential, so it gets the differential dx. I have to differentiate u. That's 1 over 2x. Remember, the derivative of a log is the reciprocal function, but the chain rule says times the derivative of 2x, so times a factor of 2. So simplifying, that's going to be 1 over x, the 2's cancel, and then I write it as a differential to match what appears in the integration by parts formula. du is 1 over x dx. To find v from dv, we have to integrate dv, so I have to integrate this power. That's not very hard to do. We just go up a degree and divide by the new degree. And that's all on the side. We then run the integration by parts formula out. It's u times v minus the integral of v du. And we just fill in those blanks now. So u times v is the natural log times the power minus the integral of v du. V is the power, and then du is 1 over x dx, so that just goes in for du there. Notice that the integral on the right-hand side has no more logarithm in it. Because the derivative of logarithm is somehow much simpler, it's this reciprocal function, it made our integral over here much more manageable. In fact, there's no more logarithm, it's a purely algebraic expression over here. Let's just clean up and simplify. I've got 1/6 x to the 6th times the log. And then in the integral I have a factor of 1/6. I put that outside, and notice that a power of x will cancel here to give us x to the 5th. Just rewriting the first term now, and then integrating x to the 5th. That gives us x to the 6th over 6, and the only thing really left to do is to clean up those constants there. And there's your antiderivative.